In problem 12.1, we're given a share price starting of $79 a share price finishing the year of $88 a share, and during the year we've paid a dividend of $1.45 a share. What is the percent total return? We know that percent return or percent R is equal to dividend yield plus capital gains yield. So we're going to take the annual dividend divided by today's stock price, that's your dividend yield, plus capital gains yield, P1 minus P0 over P0. This is your price appreciation or depreciation during the year, called capital gains yield. Very simple problem. Total return is composed of these two elements. So I take $1.45 divided by my starting share price of $79 per share. And then my capital gains yield is 88 minus 79 over 79. P1 minus P0 over P0. So I have a $9 price appreciation in the stock. And I divide that by $79 starting price. I get a total return of 13.2278%. And there's your answer to problem 12.1. In problem 12.2, same givens, $79 a share, starting price, $88 a share, ending price, $1.45 annual dividend. We want to know, what are these two components? What is the dividend yield and what is the capital gains yield in this problem? Obviously the two pieces must add up to 13.2278% that we calculated in the last problem. So dividend yield is D1 over P0, $1.45 over 79, and I get a dividend yield of 1.8354%. And simply, again, I take the $9 price appreciation or capital gains yield, divide by $79 to get the capital gains yield. So I take 9 over 79, and I get 11.3924%. If I add these two pieces up, dividend yield plus capital gains yield, I should get the original answer, 13.2278 total return, because percent return is equal to dividend yield plus capital gains yield. There you go, there's your answers to problem number 2. In problem 12.3, we have a similar problem, but this time we're not as happy an investor. In 12.1 and 2, we had a price appreciation. In this case, we're going to have a price depreciation down to $71 a share by the end of the year. We're still starting at 79, beginning of the year, still paying a dividend of $1.45 a share over the course of the year, but our stock price goes down. In this case, what is the total return? In this example, same equation, total percent return is equal to dividend yield plus capital gains yield. The dividend yield is still the same, $1.45 over $79. However, this time capital gains yield goes down. It's 71 minus 79, so we have a loss of $8. Divided by $79, I get a capital gains yield of negative 10.1266%. Doing the math, so this time I'm not as happy an investor. I still get that nice dividend of almost 2%, but this time my stock price goes down. My total return then is equal to negative 8.2911%, 8.2911, and there are your two components, dividend yield and capital gains yield. There are your answers to problem number 3. Problem 12.4 is a very interesting problem. Now we're going to look at bond increases and bond coupons, similar to a stock price increase or decrease in a stock dividend. So we're going to turn the stock problem into a bond problem. We bought a 7% coupon bond 1 year ago for $970. That means it's paying us $70 coupon, 7% of 1,000 face value. The bond sells for $940 today, so it's gone down. $1,000 face value, as usual. What is the total dollar return? What is the percent R or nominal rate of return? And what is the real return? And in this case, if we're using Fisher effect, Dr. Fisher likes to use the large R for total nominal rate of return. So let's look at some equations. Our total dollar return is the coupon we're going to get plus any capital gain or loss on the bond. Did the bond go up or did the bond go down? So the coupon is similar to the dividend that we receive on the stock, and the capital gain or loss is similar to the price appreciation or depreciation. That we see on the stock. The coupon received is the coupon rate times face value. As I said, it's $70, 7% times 1,000. The total return is dividend yield plus capital gains yield. And in this case, we're going to pose that as large R because that's the way Dr. Fisher likes to show it in the Fisher effect. And here's the Fisher effect equation. 1 plus big R equals 1 plus little r, 1 plus real times 1 plus inflation. From chapter 7, we learned this. We learned that this is the Fisher effect. So let's get some answers. Coupon received is 7% of 1,000 or $70, similar to a dividend received on a stock. And then our capital gain or loss. The bond started at $9.70, went down to $9.40, so we have a $30 loss on the bond. So our total dollar return is $40. $70 of coupon minus $30 loss on the bond. What is the total nominal rate of return? Big R, as Dr. Fisher likes to call it. Similar to D1 over P0, or the coupon received over the original bond price, plus any bond appreciation or depreciation. In this case, it went down $30 divided by the original price of $9.70. I get a total dollar return on this bond of 4.1237%. That's my total return, big R. Now, what is a real return if inflation is running at 3%? Does inflation weed into that total return? 1 plus big R, so 1 plus 0.041237 divided by 1 plus H will give me my R. And I'll get a rate of return, a real rate of return on this bond of 1.0910. We knew that the answer should be about 1.1% using the approximate Fisher effect. Big R equals approximately R plus H. And we can subtract the from the 4.1237, the 3% inflation. So we knew our answer should be approximately equal to 1.1237%. And we found out exactly that it's equal to 1.0910%, not a bad guess for an approximation on the approximate Fisher. There are your answers to problem number 12.4. In problem 12.5, we want to know what is the average annual return, 1926 to 2013, on large company stocks, according to the Ibbotson and Singfeld study. What is the answer in nominal terms or total? So nominal means total. And then also in real terms, once we take away inflation. So we need to look at what inflation was going on from 1926 to 2013. We can find these in the tables in our text. The equation is the Fisher effect, discovered by Dr. Irving Fisher. 1 plus big R, 1 plus nominal, or total return equals 1 plus little r times 1 plus H being inflation. So if I'm solving for R, the percent R, big R, is 1 plus little r times 1 plus H minus 1, just bringing the 1 to the other side. And the real rate of return, if I solve this for little r, I get little r is equal to exactly 1 plus big R over 1 plus H minus 1. So the average annual return from our book for large company stocks 1926-2013 is 12.1%. That's per Dr. Ibbotson and Singfeld in their study that they update annually. The average inflation rate from 1926 to 2013, also from the table in our book, is 3%. So the approximate Fisher effect would be little r equals big R minus H. To do the approximation, I take big R of 12.1% minus H of 3%. I get, so my answer should be approximately 9.1%, subtracting those two. That's the Fisher approximation because R times H is small if I multiply this Fisher effect out. So I can approximate my answer at 9.1%. What's the exact answer? Well, 1 plus 0.121 divided by 1 plus 0.030, and I get a real rate of return exact Fisher effect of 8.8350%. You can see my approximation is not bad. I approximated 9.1 in my head by quick subtraction. The exact Fisher effect answer for the real rate, 8.8350. There are your answers to problem number 5. In problem 12.6, I wanted to know what is the average annual return from 1926 to 2013 on long-term government bonds, and then what is it on long-term corporate bonds. So those are the two bonds I'm going to get when I buy a bond, on average, over the years. Again, using Ibsen-Sinkfeld study and the Fisher effect. I'm going to calculate the total nominal, or dig it up out of the book in the table, and I want to calculate what are these in real terms once we back off inflation of 3%, which we've seen inflation has averaged over the period 1926-2013, according to Ibsen-Sinkfeld. So first of all, looking in the book, in our textbook, in their study, they calculated that the average annual total return for long-term government bonds was 5.9%. You're going to get about 6% on average when you buy a government bond over the years. And similarly, for long-term corporate bonds, we see they returned about 6.3%, a little bit higher, a little bit more risk. And those are your total answers, or your nominal returns on long-term government bonds, on long-term corporate bonds. Now, if we subtract off the 3% inflation, what will my real returns be? My percent of little r's for governments and for corporates. Let's do the approximation first. I can simply take 3% inflation off of this 5.9, so my approximate government bond should give me a real return of 2.9%. If I do the math, 1 plus total return 1.059 divided by 1.03, I get an exact Fisher effect for long-term government bonds of 2.8155%. Not a bad estimate of 2.9%. Same similarly for corporate bonds, I can get an approximation of 6.3 minus 3, or 3.3%, just by taking big R minus H. And then my exact 1 plus big R, 1.063, divided by 1 plus H, 1.030. I get an exact Fisher effect for corporate bonds of 3.2039%. Very close to my 3.3% approximation. And there are your answers to problems 12.6. In problem 12.7, we want to calculate the average returns, the variances, standard deviations for two projects, Project X and Project Y. The average, we're going to go through a 5-step process, of which there are 6 steps, first of which we're going to convert all percentage returns into decimals before we do any mathematics, and then we'll start with the 5 steps in the normal process to calculate aimed at standard variance and standard deviation. So the average is the summation of all the returns divided by t observations. So if you have 5 observations, we'll divide by 5. The variance is summation of the deviations squared divided by t minus 1 observations, because we have small sample size here. And the standard deviation is simply the square root of the variance. Let's do Project X first. You have 5 returns, 15%, 26%, 7%, minus 13%, and 11%. What is the variance and standard deviation of these, and what's the measure of the volatility, and which of the projects is more volatile, Project X or Project Y? Step 0, change all the percentages into decimals. So 0.15, 15% becomes 0.15, 26% becomes 0.26, 7% becomes 0.07. 13% becomes minus 0.13, and 11% becomes 0.11. Step 0, convert all percentages to decimals before doing any mathematics. Step number 1, calculate the average. So once we have our decimals, we want to calculate the average. To do this, I need to sum all of the returns divided by t observations. So my summation is 0.46. If I add these 5 numbers up, I should get 0.46, and then if I divide that by 5, I should get an average of 0.092. Step 1, calculate your average. Now what I want to do is calculate the deviation. Take the returns minus the average to get the deviation. So 0.15 minus 0.092 equals 0.0580. 0.26 minus 0.09 is 0.1680. You have to be careful of your signs too. 0.07 minus 0.092 is minus 0.0220. minus 0.13, minus 0.092 is minus 0.2220, and then 0.11 minus 0.092 is 0.0180. If I've done my deviations correctly, they should all add up to 0. And that's one checkpoint. If your deviations do not add up to 0, then you've done something wrong. Step number 2, calculate the deviation. Step 3, square them up and sum them up. Square the deviations to eliminate the negatives and then add them up. So square them up and sum them up. 0.0580 squared is 0.0034. 0.1680 squared is 0.0282. Minus 0.0220 squared is 0.0005. Minus 0.2220 squared is 0.0493, and 0.0180 squared is 0.0003. Add up all these, square them up, done, and sum them up. Summation of all these square deviations is 0.0817. Step number 3. Step number 2, calculate your deviations. Step number 1, calculate your average. So we're through the third step. Now we need to calculate the variance and the standard deviation. The variance is simply the sum of the squared deviations divided by t minus 1 observations. So I take my 0.0817 as the sum of the squared deviations divided by 4, 5 minus 1 or 4 observations. I get a variance of 0.02042. 0.02042 is my variance, and my standard deviation is the square root of that, 14.2899%. Or 0.142899. So there are your answers to Project X. We do the same exact thing with Project Y. We calculate the step 0, we take and turn everything into a decimal. We calculate the average of these 5. That's step number 1. Step number 2, I subtract the actual minus the average, so 0.21 minus 0.118 equals 0.0920, 0.36 minus 0.118 equals 0.2420, and so on down the line. Calculate my deviations in step 2. They should all add up to 0 if I've done my work correctly. Then I square them up and add them up. So 0.0920 squared is 0.0085. 0.2420 squared is equal to 0.0586. 0.0120 squared is equal to 0.0001. Negative 0.3780 squared is 0.1429, and 0.0320 squared is 0.0010. I square them up and sum them up. I get a summation of the square deviations of 0.2111. Now, step number 3, square them up and sum them up. Step number 4, I calculate the variance by taking the sum of the square deviations divided by t minus 1 observations, so 0.2111 divided by 5 minus 1, I get a variance of 0.05277. Then I bring that down and take the square root of that in step number 5 to get the standard deviation. So the square root of 0.05277 is 22.9717%. And then we can compare these two projects and see very clearly that Project Y has a higher standard deviation and a larger variance, and therefore is a more volatile project. There are your answers to problem 12.7. In 12.8, we have a challenge question, the third part of which will turn out as a challenge. We want to calculate the average return, variances, and standard deviations for large company stocks and treasury bills from 1970 through 1975. We get these values for these returns from the table in the book. And I post them here also. And we also want to calculate, as a challenge part of this, what is the risk premium for each of these years? And then calculate the variance and standard deviation for those. We'll do those in a minute. The equations are: the average is simply a summation of all the returns divided by t observations. In this case, we have 6 years of observations. The variance is summation of the deviation squared divided by t minus 1 observations. And Standard deviation is square root of the variance as always. So just like in the last problem, we're going to list the returns and then go through the 6-step process. So the first step I've already taken care of. I've turned the percentages to decimals. Step number 1, then I'm going to calculate the average. So I add up all 6 values and I get 0.3330. And then I divide that by 6 and I get an average value in step 1 of 0.0555. Step 1 to calculate the average, 0.0555. Then I'm going to calculate the deviations by taking each actual return minus 0.0555. So 0.0394 minus 0.0555 is minus 0.0161. Be careful of your sign. 0.1430 minus 0.0555 equals 0.0875 and down the list. I subtract this 0.055 from each of these 6 values to get the deviations. Summation of my deviations must equal to 0. If it does not, go back and start again. If it does equal 0, I proceed to step 3, where I square them up and sum them up. So minus 0.0161 squared is 0.00025921. You're going to be dealing with 6 and 8 digit decimal numbers, so set your calculators to the 8 decimal places, set your Excel cells to 8 decimal places to capture the full accuracy of these numbers. 0.0875 squared is 0.00765625 and so on down the list. I simply square the deviations and then add them up. The summation is 0.26983486. This is the sum of squared deviations. Now to calculate my variance, I take that number divided by t minus 1 observation. So 0.26983486 divided by 5, which is 6 minus 1. I get a variance of 0.05. 3966972. 0.053966972, and then I take the square root of that to get the standard deviation. I get a standard deviation for large company stocks of 23.2308%. 23. So a lot of volatility in these years as measured by the standard deviation, a very high standard deviation. Now let's look at T-bills over those years. T-bill returns from our book are 6.5%, 0.0436, 0.0423, 0.0729, 0.0799, almost 8%. Some very high T-bill returns. Must have been a period of high inflation in the years 1970 through 1975, and indeed it was. Step number 1, add these returns up. I get 0.3624, and then take the average, divide 0.3624 by 6, and I get 0.0604 is my average. Step number 1. Step number 2, calculate the deviations between these actuals and that 0.0604. So 0.0650 minus 0.0604 equals 0.0046, and on down the line. Calculate the difference between these actual returns and the average to get the deviations. Again, the deviation should add up to 0. In step number 2, check it, make sure it adds up to 0, then you may proceed. Step number 3, square them up and add them up. So 0.0046 squared is 0.00002116. Minus 0.0168 squared is 0.00028224, and so on down the line. Square them up and sum them up, and I get 0.0117040 as the sum of my square deviations. Step number 3. Divide that by t minus 1 observations, or 5 observations, and I get a variance for T-bills of 0.00023408. And then I take the square root of that to get the standard deviation for T-bills, and I get 1.5300%. 1.53% is my standard deviation, so very little standard deviation, not very volatile, even though the rates are very high. The challenge part of this problem is to calculate then the risk premium. What is the risk premium I demand above and beyond the T-bill rates if I invest in large company stocks? So simply to get the risk premium, I'll let this up to you as a challenge, I take these returns and subtract the T-bill or risk-free rates. 0.0394 minus 0.0650, 0.1430 minus 0.0436, and so on, and calculate a new set of returns called the risk premium, for these 6 numbers, and then do the deviations, squared deviations, sum them up, go through these steps and calculate the risk premiums, calculate the variance, and calculate the standard deviation of the risk premium. That's your challenge part of this problem. I'm not going to do that. A couple other answers. Is it possible to have a negative risk premium before an investment is undertaken? The answer is no, it's not possible, because investors demand compensation for high risk. And then finally, can I have a negative risk premium after an investment? Yes, that is a possibility. The risk-free rate is very high. A good example is 1974, where I have a negative large company return, large company stock return. So where I have either or a high T-bill rate, high rate of inflation, and a nominal rate is unexpectedly low, so I could have a negative risk premium before an investment is undertaken. There are your answers to 12.8.